Hello, can you see my slide?
Yes, we can see your slides.
Yes, so thank you. So hi everyone. Welcome to Hackathon Awards and the celebration at the University Paris-Saclay. I'm being the lead of the organizing team. The hackathon took place in the end of the full week of courses, programming practice, industry talks during the Qiskit Fest 2025 at the Université Paris-Saclay. In the hackathon, the participants has opportunity to apply what they learn throughout the week of training. The hackathon is organized by our team, Biranson team. We are 8 young researchers across the world from Paris-Saclay, Oxford, KAIST, Leuven, New Delhi, and Riken. We're excited to contribute to the very positive energy to the quantum community. And the hackathon is sponsored and partnered by University Paris-Saclay, of course, IBM Quantum, Unitary Foundation, Entropica Labs, Alice and Bob, Quandela, and Akura. Okay, for a very quick reminder, the challenges are announced on 21st November. And the participants had 1 week to complete and submit their project. And today, I'm very happy to be here to announce the winners. All the other information you can find in official hackathon website of Akura, showing in the middle of the screen. All right. We have 3 challenges provided by our hackathon partners, Quandela and Tropica Labs. Quandela proposes 2 checks to predict the option pricing using either quantum random walk or quantum machine learning. The participants have to compare to the predict results to the expected output provided by Quandela. As lastly, the participants can choose to bring their own code to Loom Design on Entropica Labs platform with quantum error correction. All right. And this check is open-ended creativity check, offering a total freedom to achieve any valuable results. And the hackathon projects are managed using Akura platform. So what the winners will win if they complete, if they win the challenge, they win the prize. All right. So we have 2 technical prizes for those who submit the most insightful solutions. 500 euros for the first place, 200 euros for the second place. And since one of our checks is based on creativity, in this case, we're offering a creativity prize for participants who achieve the most vital posts about their results on the social media. All right. So what will be the criteria? What will be the criteria? Okay. For example, for technical crisis, the solution should be correct, first of all, and then it should demonstrate the high quality. All right. And we encourage the participants to attempt something new, creative, and unique. And also, the solution it should be useful and maybe to give an idea to solve similar but more complex real life problems. And finally, the presentation should be clear, well delivered. And the criteria for the viral price is a little bit different. First of all, of course, the solution should be correct as well as creative. And of course, the solution must to be shared on the social network and um, it is collected the most views and likes. It proves it's really viral on the social network. All right, so let me share about our jury members. We have four jury members. First of all, Dr. Leonardo de Silvestros, head of interaction at Anthropica Labs in Singapore. He is an expert about quantum error corrections. Secondly, Dr. Jan Bojet is an independent researcher in quantum computing. He has experience as mentor in a one series GenQ hackathon. And thirdly, Dr. Mona Lisa Singroy is an is a quantum algorithms engineer at PlanQC in Munich. She is an expert about quantum random walk in finance. And lastly, Dr. Luhaila Inan is postdoctoral associate at New York University, Abu Dhabi, and a research team lead at eBrain Lab. Was an organizer, mentor, and also jury members for the world-class hackathons over the world. For example, recently, the Q Innovation World Challenge 2025 at Qatar. All right, so let's move forward. Let's move on to the most important part of my presentation. So that is the reason why we are here. We are here to meet our winners. All right, let me introduce first our winner for the communication award. The team who achieved the most viral posts about their results, about their solution on the social network is Team GQ. They collected more than 12 likes and numerous views on LinkedIn. And
Are you interested in
let's see
finance,
why.
technology, quantum computing, or honestly just curious about the future, especially markets? Well, take everything you know about classical pricing models and just place it gently aside because we're about to step into the new era. This is our project, ZyQ Labs Quantum Option Pricer, and we're going to tell you about something we built where you can enter normal market inputs, stock price, volatility, maturity, interest rate, and behind the scenes, it triggers real quantum random walk and returns a full price comparison against black skulls. But before we show you what we created, Zach is going to take you through where we started with our algorithm, where it went, and what we ended up with.
So this is an overview of how we simulated stock price and call price using a quantum random walk. So to begin with our goals and motivations, our goal is to use quantum circuits to predict option prices in a certain amount of time that you can choose. And we want to align this predictive capability with the known Black-Scholes model for constant volatility and interest rate. And we want to do this because we think quantum random walks are a more complete and quick way of predicting stock price, because currently classical finance uses Brownian motion. And so to begin with our model mechanics, we began by creating the grid, which is our structure, our underlying structure of our quantum random walk. So the way we did this is we created a logarithmic grid because at maturity t, the log of the stock price is normalized. So you can take uh, a certain standard deviation and you can normalize it. And then you can create a logarithmic grid, which is more natural because the stock price scales multiplicatively and not additively. So we did this by creating the grid with spacing of 2 to the number of qubits we have, and then using this formula to essentially calculate the stock price at every level in the grid. And of course, quantum mechanically, each level corresponds to one basis state. So to do the walk, we essentially created a biased quantum coin using a CRR model for our diffusion, but instead of using root, this is the standard model. Instead of using root T over N, we swapped it for just N because quantum systems diffuse much quicker. And then we translated this to a rotation Ry of theta, where we choose theta to give the probability that the state increases. So then we apply Ry of theta to the initial state to essentially split it into a superposition with the probability of the state increasing as root probability up times the state, and then the probability of the state decreasing as root probability down times the state below it. And you apply Ry of theta n number of times to create the complete superposition with all the probabilities tied to it. So this would be the second state. And then once you complete this process, you collapse the whole wave function or the superposition into one state that is computed by taking a random state at the probabilities attached to the states. So to get results, we collapse the superposition 4,096 times. In our case, you can change this number. It just will make it slightly more accurate if you increase it or whatever. It doesn't much matter. And then we can calculate the expected value of the stock price, the expected call value of the call payoff, and then the call price using these formulas. So, and then we just compare it with Black-Scholes. So this is our result currently. Well, one of the result, of course, this number will change every single time because you take a different expected value. But this is at 8 qubits and 31 steps with a standard deviation of 4. You can change these numbers to get different results. This is just what we found gives the best result. And you notice that our random walk call price is much lower than the expected Black-Scholes call price. And this is likely due to the truncating of the distribution tails, because we only utilize 4 standard deviations, where Black-Scholes will utilize the entire continuous distribution. So the extremities are cut off in this case. So other characteristics, technically we have implemented a reflecting boundary. So when the superposition reaches the ground state or the max state, it will reflect and go either one above or one down. But we found much better results by effectively introducing an infinite boundary by making the bounds much higher than where the superposition can reach. And then, of course, the results can vary on number of qubits and time steps. And this seemingly has a relationship in the ratio of the qubits, is what we found. And then these are two sources that we use to base our model off of, mostly Orel, some of De Becker. And then thank you to our following sponsors.
Awesome. Thank you so much, Zach. And now we're going to show you what we made. So I'm going to share my screen and take you to our web application. Awesome. How much time am I working with here, Zach?
5 minutes until submission deadline, like a minute.
Amazing. So here's our website. We have users we have given users the capability to change initial stop price, strike, volatility rate, maturity, qubits, number of time steps, and this is all utilizing the algorithm where risk neutral drift. We have auto computed log space price bounds and flexible up down movement, a new speed corrected log movement model. Yeah, so it's really exciting. We click run here and it compares everything with the traditional financial modeling and gives you the price distributions down here. So yeah, I'd love to share with you guys a little bit of code, even though we're running low on time. Let me stop screen sharing.
Get reason very quick.
Very quickly. So let's start with the back end.
And he was like, doing like, he's having fun with the snow. Yeah, he's like really driving. And everyone's like,
Zach, do you want to?
crazy. He's like, no.
Okay. So starting with main, this file turns the quantum engine into a real API. It exposes price endpoint that takes user inputs, runs the algorithm walk, runs black skulls using skip_b.stats, and returns our quantum call price, black skulls call price, expected ST from the walk, drift calibration, full histogram, terminal probabilities, all of that. We have let's see if I can find everything. We're running low on time. We have our app here. For the part I'm most okay, so input form, results panel, histogram. For the part I'm most excited about is our front end. So this is our React and TypeScript interface. It's not just a form, it's entire experience. It handles the UI state, loads our animation, fetches the back end, renders results dynamically. Yeah, and it just lets people play around with our code and include volatility, qubits, and steps. Yeah. So we've had a lot of
Okay,
fun with this.
that's all the time.
That's all our time. I don't know where to go.
Yeah.
Thank you so much.
So it's very interesting, right? Let's congratulate again for the team GQ. And unfortunately, they are based on USA. They are not able to attend our ceremony, our two-day ceremony. So I will contact them later to get their thought about like their feeling about winning this prize. And let's moving on to a more valuable prize. All right. So note that it could be the winner. It could be Team ZQ again, or it could be another team. And also, yeah, as you can see that the last winner is on the quantum random walk project, and for this prize, this could be quantum random walk project again or another project. All right. And the winner, the second place of our hackathon is belong to Matteo Piccolini. So the same, let's dive into the solution of Matteo.
Hi, I'm Matteo Piccolini, and this is my project for the Candela Challenge track number 2 presented at the Qiskit Fall Fest 2025 Hackathon. The goal of this challenge is to develop a quantum machine learning framework which, given a dataset provided by the organizers, is able to reliably predict the future prices of swap options over the next 2 weeks. I chose to employ a quantum reservoir computing model with a single reservoir, following the main reference reported in this slide. The quantum reservoir computing model exploits memory effects in the dynamics of a fixed quantum system called reservoir. The crucial difference with standard neural network is that the reservoir parameters are not trained. That means that the learning occurs only during classical post-processing of measurement results. The reasons why I chose this model is that its temporal dynamics allows for great prediction capacity for time series. It requires no computational burden of training neural networks, and different implementations of this model have already been conceptualized for different physical platforms. The quantum reservoir computing model divides the qubits into two subsets, denoted as input qubits and hidden qubits, all initialized in the zero state. Features at time t are predicted from the past k features, and I fixed within this job k equal to 3. I employed angle encoding to encode one feature per qubit using a standard minimum-maximum normalization. The total system is then left to evolve with a fixed Hamiltonian h for a fixed time tau. After that, the input qubits are reset, whereas the hidden qubits are not reset and preserve dynamics memory. This process is repeated until the temporal step t-1, obtaining k layers. After that, we do not reset the input qubits, but instead we measure all the qubits, gathering the expectation values for each qubit of the Z operator. Finally, we train the measured data with the target data, obtaining the weight matrix W from linear regression. Let us now move to my project. I began with managing the data provided by the organizers. Indeed, we were provided with a dataset containing 224 features as combinations of tenors and maturities. This would require too many input qubits in the circuit to encode one feature per qubit. Therefore, I had to firstly reduce the number of features, and I did so by using the principal component analysis compression. I obtained in this way 3 principal component features which capture the highest variabilities of the data. I then split the dataset into a 70% of training dataset and 30% of test dataset and prepared the input data for the quantum circuit. I employed 3 features and 3 temporal layers, thus resulting in 9 parameters required for the circuit in order to predict the principal component features at time t. I finally used the rolling window approach where I started from t equal to 4 and I repeated the whole process for every subsequent time. As a second step, I created the quantum circuit. To do so, I started by encoding features into the input qubits with angle encoding. For the evolution, I chose an Ising Hamiltonian with all-to-all interactions between the input qubits and the hidden qubits, without intrasect interactions. The resulting evolution operator is the one reported in this slide. To implement it, I used its Trotter approximation to first order. You can notice that in this way the implementation only requires 2 qubits XX rotations and single qubit Z rotations. Some parameters are free and can be defined by the user. These are the evolution time tau, the magnetic field strength nu, and the number of hidden qubits. In this project, I fixed the evolution time and the magnetic field strength to 1, using 7 hidden qubits. As a third step, I ran the quantum circuit. I designed my code so that the user can decide whether to employ a real backend or a simulator. I employed a simulator due to runtime limitations on real IBM hardware linked to my account. I obtained a circuit depth of 36 without noise model implementation and of 222 with simulated noise. I indeed decided to simulate noise, taking it from the real IBM Torino backend. I then employed the Qiskit runtime primitive sampler with a fixed number of shots fixed to 10,000, and I finally reconstructed the expectation values of the Z operator from the measurement results. Later on, I used the measured expectation values to train the model with the Ridge linear regression method. I finally tested the results on the test part of the dataset, obtaining the plot that you can see in this slide. I proceeded by generating future predictions over 2 weeks as required by the organizers. So I forecasted the next 14 days using the train weight matrix. Then I reverted the principal components normalization and decompressed them, finally saving the dataset. I evaluated the precision of the employed model, computing the mean square error of the 3 principal components on the test set. I then compared the obtained precision with the one obtained using a classical gradient boosting method. The results of such comparison can be seen in this slide. You can notice that the quantum method performs better in computing the first principal component and worse in computing the other 2. So this was a brief summary of my work. You can find in this slide a link to my GitHub profile with the repository containing the project and a link to my LinkedIn profile together with my email. Thank you all for the attention.
Great. I saw that, Matteo, you are here, right? Can you put your camera?
Hi, can you hear me?
Yes.
Yes, I'm here.
Yes, let me put. Spotlight.
Okay.
So thank you, Matteo.
Thank you very much for this opportunity.
Yes, congratulations.
It's been
about it's very important, yeah.
Yeah, thank you. It's been super useful to learn quantum reservoir computing, and it's been very fun for me to dive into it. So I'm super happy of the prize too, of course, and it's been great. Thank you.
Thank you. Can you share some feeling, some thought, and
Sure.
What do you think about the challenge, and what is your advice for all the all the participants for the upcoming hackathon?
Okay, so do you want to see the code too, or just some comments on the hackathon in general?
No, it's just in general. What do you feel now? Because I see that you are very happy for now.
Yeah, I am. No, what I liked the most was to have to learn something new, because I was already accustomed to quantum computing, but not so much to quantum machine learning. So having to learn a new type of model, it's been something that as a physicist I really appreciated. It's been weird at the beginning because dealing with finance tools, which is something I never met in my life, it's been another interesting occasion to learn something new. So you asked for suggestions, and I think that the main suggestion for everybody into quantum computing remains stay curious and go on learning, because that's one of the most amazing things of our job or student life, according to who you are.
Thank you. Thank you.
Come.
You told me that finance is not your field, but you got very high scores from the jury members.
Yeah, from the
But
project.
yeah, so thank you. Thank you for your contribution and keep shining.
Thank you.
Thank you. Yes, so let me go back to my presentation. Now that is the very important moment. The winner, the first place of our hackathon, Qiskit Phone Fest 2025 hackathon at Université Paris-Saclay, is the one who provided solutions for both challenges, the one who worked very, very hard. And the first place is belong to Dora King. Of course, you are very serious, very curious about his solution. Right now, I'm sharing the projects that have Dora King to earn the highest score from our jury members.
Welcome to the video on bringing the 832 color code to Loom, a submission for the Qiskit Fall Fest 2025 Paris-Saclay Hackathon by Quantum Pioneers. The challenge was the Bring Your Own Code challenge. We targeted the 832 smallest interesting color code, which encodes 3 logical qubits into 8 physical qubits. We used Loom, an open source framework for defining quantum error correction codes and generating simulation circuits. Our implementation strategy involved creating a color code 832 class inheriting from Loom's block class. We mapped the cubic structure to a 2D square lattice for compatibility with Loom's tools. We also defined X-type and Z-type stabilizers corresponding to the faces of the cube. A technical innovation was the implementation of automated operator finding. This solves the problem of manually defining logical operators, which can be error-prone. By using ~find_logical_operators, we mathematically derived valid operators, guaranteeing strictly valid canonical commutation relations. For verification, we performed a memory experiment using the ~verify_832.py script. The results showed perfect measurements for logical 0 greater than and logical 1 greater than, and an expected 50-50 random distribution for the superposition test. We visualized the code using a custom matplotlib script, mapping physical qubits to 2D coordinates. Stabilizers are shown as colored faces, where red is X and blue is Z, allowing for visual verification of qubit connectivity. In conclusion, we successfully integrated, verified, and visualized the 832 code in Loom. Rigorous validation and automated operator finding are crucial for quantum error correction code development. You can find the resources on our GitHub page.
Right. So let's congratulate again for Dora King. And say similarly, Dora King is living in Japan, so he is not able to join us for today's ceremony. We will contact him later for the feedback. Okay, so finally, I would like to give the very special place for all of the teams completing the challenges. The prize will be very cheap. That is our hub for our team, a big hub for our team. So why it's really important to completing the challenges? Because improving is much more important than proving. And we hope that you learn a lot through our challenges for this year event. Also, we would love to encourage you to keep learning and keep growing because you are the future of quantum computing. You can continue to learn from the following platforms for example, IBM Quantum Learning, Quantiline, and also Alice and Bob, because they are totally free. And if you are those who learn more by contributing to open source projects, please contribute to Unitary Foundation, Acura, or Anthropica Labs. And very important too, don't forget to connect with our jury members on LinkedIn, because you can get further opportunities like collaboration, or if you are looking for internship and so on. It's very important to connect with them. You can get some free guidance, and also you can update important information or important knowledge about quantum computing. And finally, if you love what Birantom does, please connect us, join us. We can have a further collaborations. Our team members are from many countries over the world, but we are still going up. And finally, I would like to thank you for all of you, all the participants, on sponsors, our sponsor partners, and also our Biranton team. Thank you again, and ladies and gentlemen, Merry Christmas and Happy New Year.